So first of all, I would like to thank Professor Tajima and academician Sergey to letting me speak here at this forum on climate change and global energy issues. As a nuclear chemist, I would like to continue my presentation with the nuclear energy as one of the energy in the pool of different energy sources and how it can help to solve the global change of the zero emission. So I represent Moscow State University and Russian Academy of Sciences in Frumkin Institute of Physical Chemistry and Electrical Chemistry. So first of all, we need to define where are we now and what is the goal and how to reach this goal. So one of the aims that is on the slide is decarbonization target of 30 grams of carbon dioxide per kilowatt that was formulated by the OECD. And certainly the nuclear energy is one of the concentrated source of energy, and green sources of energy can be used to solve this, to reach this aim. I don't want to go deep into some introduction of the nuclear science and nuclear energy, as Professor Lee already did it. But I would like to stop on the few more basic things. So first of all is I would like to mention that an increased share of low carbon sources, as well as drastically reduced level of fossil fuels, work together in harmony to secure a reliable, affordable, and clean future energy consumption. This will require a large increase of all low carbon energy sources, of which nuclear is an important part. So here, the forecast of the electricity consumption growth in low carbon scenario is presented. So the question is, what would include this low carbon scenario? What would be the energy sources in the future? So according to one of the forecasts, the share of fossil fuels would decrease, as you can see it in the image in the lower part of the slide. At the same time, we have the large increase of the solar, wind, and nuclear energy. That is one of the major concentrated sources of energy with zero emission. And certainly the zero emission could be proved on the slide here as well. On the image, you can see that emission of nuclear is even less than the solar, biomass, and incomparably low compared with the coal and gas emissions. Provisions of the clean and reliable energy and reduction of the air pollution. So there are two numbers are presented here. One is the forecast of the OECD International Energy Agency saying that decarbonization scenario, electricity generation from nuclear sources increases by almost 55% by the year 2040 to 4,300 terawatts hour, and capacity grows to close to 600 gigawatts of electrical power. According to the World Nuclear Association, the Harmony program proposes the addition of 1,000 gigawatt of electric power of new nuclear capacity by year 2050 to provide 25% of electricity from 1,200 gigawatts of electrical power of capacity. So, and this is reliable numbers that could be reached, because even in year 1940, 84, 31 gigawatts of electrical power in nuclear energy was added by a single year. So this is where we are now. So this is the world nuclear power generation. As you can see, this is quite amazing, but Chernobyl accident, you can see the point here, it does not really affect greatly, it even doesn't affect at all the increase of the share of the nuclear generation worldwide. And the decrease due to Fukushima accident and in the year 2011, we can see it here. It's not really dramatic, and in few years we get back to the same numbers that were reached in the year 2010 before the Fukushima accident. So this is just basic numbers where we are again now. The first commercial nuclear power stations started in operation in 50s. A first commercial nuclear reactor in Eurasia was launched in 1954 in Soviet Union in Obninsk. So all the technologies that were used at the early days for in the weapon programs, they were used also for commercial nuclear power stations. Nuclear energy now is about 10% of the world's electricity from about 440 power reactors. Nuclear is the world's second largest source of carbon-free energy sources. So it's about 29% in year 2018. And now it's about 50 countries somehow utilize nuclear energy in about also 220 research reactors. More than 50 new reactors are under construction, and you can see there's the share of nuclear through the different years, and you can see that there's relatively large increase in the share of nuclear for Asia. This is few slides with the world map showing, the first one is showing the change that we observed in year 2019 for the annual discharge in fossil fuel consumptions. You can see there's a large increase in China with large decrease, but smaller than increase in China, decrease in United States, and some smaller decrease in Russia. But the truth is that in China, if we go further, the low carbon energy generation is also increased in China. So this is the country that has dramatically increased the energy demand, and both from different sources, from fossil sources, from low carbon, and also from nuclear. As you can see in China, the addition is 130 terawatts hour compared with only 9 in Russia and minus 1.7 terawatts per hour in United States. Before going more into the details of this new strategy for nuclear energy generation, some more basic but very important facts. So according to the IEA World's Energy Outlook, the cost of electricity in China from onshore wind, solar panels, and offshore wind is respectively 60, 50, and 140 higher than that from the nuclear. So means that in terms of the economy, nuclear is preferably compared with wind and solar sources of energy. According to OECD, Nuclear Energy Agency, a mix relying primarily on nuclear is the most cost-effective option to achieve decarbonization target of 50 grams of carbon dioxide per kilowatt of power. Important thing that the average dose rate for the population living near coal power plant is about 40% higher than for the populations living in the near nuclear power plant. Certainly, I consider only non-accidental operation of the nuclear power plants. Raw material base, uranium is only 5% of the net cost of the nuclear power generation, compared to about 75% of the crude oil and gas in the fossil fuel energy generation. So it means that these markets are much more volatile and they dependent on the global prices on the fossil fuels. So this is just an example. The particles, why the population living close to the coal plants, they get higher dose rates. So one of the excellent examples coming from the Rod Ewing, who's actually foreign member of Russian Academy of Sciences. So they detected the particles in Detroit in coal plant of carbonaceous matter similar to fullerenes, and nanocrystals of uranium dioxide was embedded inside the structure of this fullerenes. Means that they can be easily transported to the air through the large territories and population living near these coal plants. They breathe this air, and this affects the lungs, and this affects the dose rates of the people living near coal plants. So what is the problems associated with nuclear generations, and the problems where chemists, physicists, engineers should solve? Certainly the social barrier, the reactor safety issues are very important, and the safety of spent nuclear fuel and radioactive waste management programs. This is really large social and public acceptance problem. Nuclear security and non-proliferation, the issue that we cannot escape. So this is very important. Technological infrastructure and waste management, and certainly the option for geological disposal. The option between the closed nuclear fuel cycle, where we have the reprocessing, and open nuclear fuel cycle, where we have the once-through option of the spent nuclear fuel. So this is just an example. Considering the geological disposal, there is no single license deep geological disposal in the world, just because we need the forecast, we need the safety assessment in the years of 10 to 6 or even more. So you can see this is a toxicity of the spent nuclear fuel, and different contributors of the contributors to this toxicity. You can see why Russia and many other countries, they go to the closed nuclear fuel cycle, where we have the radiochemical technologies to separate different fractions, different radionuclides from the nuclear fuel cycle. You can see how the picture is changing when we separate plutonium isotopes. Here, this is how it changed when we separate americium isotopes, and here how it looks like when we got off neptunium isotopes. So it's only iodine 129 and technetium 99 that is responsible for long-term radiotoxicity, and this radiotoxicity is lower than the radiotoxicity of uranium ores that start to be much more easy to license and much more easy to for the safety assessment. The main problem with the nuclear generation, with the nuclear energy, is the nuclear waste. So the nuclear waste that originated on all stages of the nuclear fuel cycle, and especially upon the reprocessing of the spent nuclear fuel in the closed nuclear fuel cycle. So this is just the numbers. But I would like to mention here that you can see the activity is very large, both liquid and solid. And you can see that if we consider volume, so the volume is mostly low level and intermediate level waste. High level waste is not that much in terms of the volume and the weight, but it corresponds to more than 99% of the activity. It is demonstrated here. We can see that liquid or solid waste, low level, is 99% in terms of the volume, but it's only, for example, 0.009 and 0.003% in terms of the activity, and vice versa for high-level waste. The volume is not very large, but the radioactivity, it's dominating. It's about 99%. So the main technological challenge is what to do with all this waste, how to treat them, and how to safely isolate them from the humans. So one of the possibilities, the closing of the nuclear fuel cycle of the new generation, where we use both thermal neutron reaction and fast neutron reaction. This is the way how we are planning to do in Russia. So this is the image of the open nuclear fuel cycle. So we have uranium mining and milling, then we have isotope enrichment and fabrication, then we have fuel that goes to the nuclear power plants with thermal neutron reactions, then we have the spent nuclear fuel and the storage. And probably in the future, when some deep geological disposal of the spent nuclear fuel will be licensed, so all this spent nuclear fuel would go to the deep geological disposal. This is how the classical closed nuclear fuel cycle looks like. So after the storage, we have the reprocessing. So we separate uranium from the spent nuclear fuel, we regenerate the fuel, it goes back to the nuclear power plants with the thermal neutrons. The problem is that we have a large volume of various radioactive wastes that are originated at the reprocessing step. This is how the closed nuclear fuel cycle with both thermal and fast reactors looks like. So it is already realized in Russia. So uranium, again, is reprocessed. It goes to the reactors with the thermal neutrons. Plutonium goes to the mixed oxide or mixed nitride fuel production. It's already launched in Krasnoyarsk chemical and mining combine. And there is the experience in fast neutron reactor operation at Beloyarsk nuclear power plant. So there is the two fast neutron reactors that are under operation at this nuclear power plant. So the mixed oxides utilizing plutonium originated from the reprocessing and uranium could be used at this type of the reactors. And this is how it would look like, I hope, in the future. So this light blue arrows corresponds to the project that we have to create. So some new reprocessing technologies would be tested, and uranium and plutonium would be also given, placed back to the mixed oxide or nitride fuel production for the fast neutron reaction. The major thing is that we would separate the minor actinides and mostly americium and neptunium for burnup. So it would be transmutation using either molten salt reactors or using heterogeneous reactor, and then geological disposal for high-level wastes that have the half-life period of about 30 years. So the new strategy based on the nitride fuel. So I'm not going deep into the details, but the properties of mixed nitride fuels is to, for example, the density is better than compared with the metallic or oxide fuels. So in this fast reactors, the dense nitride fuels are proposed as a nuclear fuel. The main challenge for the chemist, the main challenge for the radiochemical technology is that the fuel after this fast reactors would be fuels with the relatively higher burnup. Let's say about 2 times higher burnup compared with the thermal spent nuclear fuel. We expect that would be low exposure time. So it means that the spent nuclear fuel would be much more hot in terms of the radioactivity compared with the spent nuclear fuel from thermal reactors. High fission product content, so macro concentration of different fission products, and high plutonium content compared with the thermal reactors. This is the principal scheme that combines the two techniques: the pyroelectrochemistry on the head operations, where we have the very high radioactivity of the spent fuel, where we cannot use wet chemistry techniques. But after pyroelectrochemistry, we can do hydrometeorology to separate, to fractionate different components of radioactive waste depending on the half-life period, and reprocess plutonium and uranium, as I already mentioned. One of the challenging things is that we have is the separation of the elements that have very similar properties, like americium, that is a half-life period of 400 years with relatively short-lived europium and curium. So again, if we separate americium from the waste, we transmute them to relatively low half-life period fission products, we can go from the tens and hundreds of thousand years of safety to hundreds of years. So as you can see it in the image, so it means that we solve together the ecological, environmental, and also economical problems. So how we do that is the traditional techniques that we used. So based on solvent extraction, the separation factor is very low. So we need a lot of settler mixer extraction units, like 100, 150, to meet all the non-proliferation requirements. Means 99.9% of the yield for the fissile americium. So that also results in the large volume of secondary wastes. So what we do here is that we try to use different new novel extraction systems. So we start with the quantum chemical calculation for different molecules, I think hundreds, thousands of different molecules, and using DFT calculations, we try to figure out, let's say, tens of the molecules that possess appropriate properties. So selectivity, efficiency towards americium separation, stability in different media, etc. Then we do synthesis. So by DFT calculations on the supercomputers, we minimize the practical experimental work, synthesis and extraction. So we synthesize only few ligands. Then we make tracer experiments in the lab. We certainly test the radiation damage and radiation stability of these molecules. Then we do large quantities, large amount batch tests with the milligram quantities of rare earth elements, americium and curium, to see if everything is work at the same level as the tracer in the tracer experiments. Then we do experiments with
5 more minutes.
Yes, I'm almost done. Then we do technology development based on the real technological schemes at the different facilities for reprocessing. And by combining this data, we also can do deep learning. So we can have the global viewpoint of the metal complexation, database on development, predictions of the molecule properties, etc. So this is just an example of the different molecules. So there are hundreds of them, but in practice we do about maybe 10 of them. So we predict delta G. That means that the selectivity of one element like americium within the mixture of rare earth elements and curium. There is a lot of ligand design that we can do. For example, here, so this molecule, the first molecule, is quite it's not hard. So it can be moved, and we need some energy to pre-organize this molecule compared with this one. So this model is have a hard structure, means that the energy to produce the complex with americium is lower. So this molecule is much more efficient compared with the previous one. So we do also some predictions of radiation stability, how the molecules will disintegrate, and this really can be predicted, and it's well tested in the practical tests by electrospray ionization mass spec to detect radiolysis products. And by stepwise molecular design, we can go to the very selective molecules that can give us the selectivity factor of 6 compared with 1.5 with the classical TBP, for example, with a high radiation stability and relatively high solubility in technological solvents. As a result, we can separate americium with a purity of 99.9% on the yield of 99.9% that fits the non-proliferation requirements. It could be done in only 10 extraction units, 10 rinsing steps, and 3 stripping steps. So we minimize the number of steps, we minimize the number of secondary volume, and we can quantitatively separate americium with a high purity. To conclude, I would like to say that nuclear energy is the best or even the only option for practical decarbonization target of 50 grams of carbon dioxide per kilowatt hour of energy. Nuclear waste is the major challenges in the development of safe and reliable nuclear energy. New strategy based on the combination of thermal neutron reactant with cheap energy generation, with fast neutron reaction for recycling of fissile materials and burn up of long-lived radionuclides from waste. This is a new strategy, and I showed you that we are ready to launch it with, for example, with transmutation of long-lived americium isotope. So this would give us the decrease of uranium mining. This is also economic and environmental issues that are solved. This could minimize or eliminate deep geological disposal with saving only near surface repositories for the short-lived radionuclides. This is a cheap energy production. This is the possibility to use of excess plutonium that is also referred to non-proliferation issues, and this is very important. So by this, I would like to end, and thank you for your attention.
Thank you very much, Stepan. We have time probably for one question. So is somebody willing to put a question to Stepan? Maybe me. Stepan, could you tell what is now the state of the art in developing of this technology in different countries? Probably Russia goes just its own way. What about China or other countries?
Well, China would be, I think, #1 in the share of nuclear in the next maybe not 5, but maybe 7 years. So it would be #1 in the share of nuclear in the national electricity production. The interesting thing that at least 2 countries that, according to my knowledge, that is China and India, develops thorium nuclear fuel cycle. So as is already mentioned by Professor Lee, the content of thorium is higher compared with content of uranium in the Earth crust. And this is like a new ocean of possibilities for the nuclear energy generation if we also consider thorium nuclear energy production. We also can solve the non-proliferation issues because transuranium elements like plutonium are not formed at the thorium nuclear fuel cycle. So I think this is one of the future possibilities. At least 2 countries, India and China, have the projects in the thorium nuclear energy. So I think we're #1 in terms of the fast neutron reactors. As France, they had 2 fast reactors, but they were shut down. But we have very successful experience in terms of the exploration of BN 400 and BN 600 at Beloyarsk and NPP.
So thank you very much for your very interesting talk.
So can I ask a question?
Yeah. One more question, please, Valery.
Can I ask a question?
Yes, please.
Yeah, you didn't speak about accelerator-based technologies of transmutation and also breeder reactors. Do you have any opinion about these, directions?
Well, indeed, one of the options is the accelerator-driven transmutation. It's a little bit costly compared with the breeder reactors. So the 2 options are considered now based on the economy is the heterogeneous reactor. That would be a molten salt reactor that could be that could work permanently. So the fission products after the transmutation, for example, of americium, they could be separated online through pumping of the fluoride melt through some sorbents. And another possibility is to use heterogeneous reactors. So again, I would repeat that the economy of reactor-based transmutation is much better, it's much preferable compared with the transmutation using accelerated techniques.